All right, so let's talk about chapter 5. We're going to look at some thermochemistry. Now, this is going to be some review, some new stuff, right? So remember, you can pause, you can rewatch, you can email me with questions as we move forward, okay? So let me grab a pen. There we go. And move that out of the way. All right, so let's start with a brief review of what energy is. Okay, so energy is the ability to do work or to transfer heat. Energy is used to cause an object that has mass to move, is what we define as work. And if you're just causing the temperature to rise, we're going to call that heat. Okay, so hopefully that's some review from last year. In chapter 5, we're going to look at thermodynamics, thermochemistry, and the transformations and the energy associated, with the transformations of one compound into another, or one set of elements into a compound, that kind of thing, or maybe even a compound breaking apart into elements. Now, before we get into the more advanced stuff, let's again just look at some simple review. First, kinetic energy is the energy that you, the object, have by virtue of your motion. So a lot of times we write this as Ke equals 1/2 mv squared, but E sub K is also kinetic energy. Basically, as the biker goes down the hill, her potential energy is being converted into kinetic energy. Potential energy is something that we've actually already seen, right? This should look familiar. It's Coulomb's law, which we saw in the unit on bonding. So potential energy is energy that you possess just based on your chemical composition, all right, or where you are. So in the case of the biker, she's at the top of the hill. She has more potential energy than if she's at the bottom of the hill. When we talk about, the potential energy of elements, if they're oppositely charged and if they're like charged and they're close together, they have, this higher repulsion. So they would have greater potential energy based on their position relative to one another. When we talk about, in terms of chemistry, when we talk about potential energy, the thing that we are most kind of concerned with is the electrostatic potential energy, which again we saw in the chapter on bonding. When we express energy as a number, as a quantitative value, we use the joule as our unit. It is the SI unit of energy. You may see the calorie, which is still, like the slide says, in widespread use. This is a conversion that you want to memorize, right? A calorie is 4.184 joules. This is not quite the same thing as a calorie in the food that you eat. The food that you eat is a kilocalorie. So that would be 4,184 joules per calorie. So obviously a joule is a pretty small unit of energy. Oh, excuse me. Now, the second thing that we're going to look at after energy is applying that energy movement to either the system that we're studying or the surroundings that, is everything else. The system is, as I said, the thing that we're studying. So if we're looking at a specific reaction, it's going to be, say, the reactant molecules. The surroundings is going to be everything else, not directly, in that reaction. So if we're doing the reaction in a beaker, the beaker itself is part of the surroundings, okay? If we're just looking at the net ionic equation, then maybe the solution of water that the ions are suspended in may be part of the surroundings, all right? Work is another thing that we're going to see. Work is, from physics, force times distance, okay? The distance that the force is exerted, that is. And work, as we said a minute ago, is the energy used to move an object, all right? Heat is transfer of energy that just increases temperature. Remember from last year, like the spring of year 1 chemistry, we talk about specific heat. We know that heat flows from warmer objects to cooler objects, always warmer to cooler. Now, when we convert energy from, say, potential to kinetic, that's going to occur as something moves. Okay, so as my cyclist here, as she goes down the hill, her potential energy drops, her kinetic energy goes up. The first law of thermodynamics tells us that the amount of energy in the system can't change. It's neither created nor destroyed. It's conserved. So in the small scale, the amount of energy that she has right here, we're just going to say E equals X. When she gets to the bottom of that hill, E still equals X, right? It can't change. So the universe as a whole, right, the total energy confined to our universe is constant. If a system loses energy, the surroundings must gain it. If the surroundings lose energy, it must be going into the system. And so the first law of thermodynamics is usually written like this. Now, I go back and forth as to whether or not to use U or E here. In my upper level chem courses that I took in college, we always used U. The book uses E, so you're going to see E in this, in the rest of this PowerPoint, which I hate. It's U, but it's E. So there we are. Also, Q and W, the other two terms, right? So let me explain this first law. So this is the first law of thermodynamics. There we go, right there. And it says energy is conserved. So the change in internal energy is how you read that, is equal to Q stands for the energy supplied to the system in the form of heat, and W stands for the amount of thermodynamic work done by the system on the surroundings. Now, that is a really important distinction. It has to be work done by the system on the surroundings, not work done by the surroundings on the system. The sign will change based on who is doing the work, all right? So in this case, we're looking at the work done by the system that we're studying. Now, internal energy is the sum of all the kinetic and potential energies. That's another way to look at Q and W. So if you're losing energy to your surroundings, if your final answer is negative, right, then we would expect that energy to go into the surroundings. On the other hand, right here, if the final state of our system is positive, we would expect that means we're absorbing energy from the surroundings. Now, another way you can look at this instead of Q and W is E final minus E initial, right? The change in the energy in the system is equal to the final state, whatever that value is, minus the initial state. When you have the initial energy greater than the final energy, then your delta E is going to be less than 0. That means you're releasing energy into the system, right? And we have a name for that. If you're releasing energy into, if you're absorbing energy from the surroundings, so you're putting energy into the system, we call that endergonic reactions. If you're releasing that energy, we call that exergonic reactions. So we want to know those two vocab words. We want to be able to use those, but we're describing that final delta E or delta U. When you exchange energy between the systems and the surrounding, the actual exchange is either Q, right, heat, or work, and they can be lowercase or uppercase, it doesn't matter. So that's how we get to back to the first law, right? Delta E equals Q plus W. So when we look at these things, like, we want to kind of hold them as equal in our mind. Delta E is equal to the final minus the initial state of energy. It's also equal to Q plus W, right? All that good stuff. Now, when you look at the signs, you want to know what the sign conventions mean. So like for Q, if you have a positive Q, the system is gaining heat. If you have a negative W, it means the work is done by the system. So that first equation that I showed you, delta U equals Q minus W, it's saying the system is gaining some heat from the outside and it's doing work, all right? That's the sign convention. If someone was to give you this, all right, well, that's different, right? Now you're saying the change in internal energy is equal to the work done on the system minus the loss of heat, okay? So we want to make sure that we get our sign conventions right. Pretty easy one is the final one. A positive delta E is a net gain of energy. A negative delta E is a net loss of energy. So if you're absorbing heat from the surroundings, we call that endothermic, all right? If you are releasing heat, we call it exothermic. Now, this is reactions, right, that we already know about. I want you to be able to equate in your mind endergonic and exothermic and intergonic, exogonic, endothermic, and exothermic, right? Be able to kind of tell the difference. Typically, we use the gonics to talk about delta E. We use the thermics to talk about the actual reaction itself, but they are basically interchangeable. So it's not like I would mark off or something like that. State functions are a way that we have to then look at these things because there is actually no way to find that delta E or delta U. You can't know the internal energy. Like trying to calculate that is just a really, really, really complex problem. So we have to kind of approach it from a different angle. We know that the internal energy is independent of the path by which the system achieved that state. All right, what's that mean? Well, if I look at a beaker, and that beaker is 50 grams of water in the liquid state at 25 degrees Celsius, and you ask me, how did we get here? I could give you two equally correct answers. I could say we had 50 grams of boiling water, we poured it in the beaker, and it cools down, and now we're at E. Or I could say we had 50 grams of solid water, right, ice at 0 degrees Celsius, and it warmed up, and now we're at E. Both of those things are true. So since it doesn't matter the path that it got there, that is something that we call a state function, right? Internal energy is a state function. It is not path dependent. All right, what do I mean by path dependent? Okay, well, check this out. Altitude and distance traveled up a mountain is a great example of the difference between a path-related function and a state function. All right, so here's my mountain, right? And we want to go all the way to the top and put a little flag on it. Now, I have two ways I can do that. I can get in a helicopter. I'm going to try to draw the world's worst helicopter here. That's not terrible, right? There we go. I can get in a helicopter. I can go straight up. I can drive straight over. And I can plant that flag. In this case, I only traveled just that vertical elevation, right? I went straight up and straight up. Same thing, but now I got to climb. And so I've got to follow the contours of the mountain. I got to give, I got to give with it, go back and forth and back and forth and back and forth. And finally I get to the top. Well, this distance and this distance are not the same distances, right? But the final outcome was the same. So the height, the elevation of the mountain, that's a state function. It didn't change whether I measured it when I got to the top after I walked all that, switchbacks, or if I flew up there and hopped out of the air, out of the helicopter. On the other hand, the distance itself is path dependent. Okay, so internal energy is a state function. It only depends on the present state of the system. That means delta E as a whole only depends on the final and initial states of the reaction. Well, that's great for delta E. What about the other side of the equation, Q and W? See, Q and W are not state functions, all right? If you have the energy in a battery, all right, we know that delta E is the same for both of these, right? They both equal delta E. They are the same. It's the same battery. But if all I do is hook the battery up to a radiator coil and just touch the two ends of the battery, and electrons move and heat is given off, well, in this case, W equals 0. It didn't do any work. And Q equals, we're going to say 100% of the work done, right? The energy. On the other hand, if I hook it up to a fan, well, I'm still going to give off a little bit of heat, right? I'm still going to have a little bit of heat coming off this motor. So I'm going to have, a small Q, but I'm going to have a large W. They're still going to equal the same delta E. So this is a non-state function. When we look at work is usually done in a closed setting. An easy way to look at this in chemistry is to look at the work done in a piston, all right? So when you compress the gas and you change the amount of volume in there, the gas particles, right, they're pushing back. We learn that with kinetic molecular theory. So if we want to get a really accurate reading of this, how much work is our gas doing, then we'll put our piston on a sealed reaction vessel. So in this case, work is going to be equal to the negative pressure times the change in volume. So as the volume here changes, all right, I can calculate how much work the gas did based on the idea, all right, that the only work being done is pushing on its surroundings, okay? So the only work is work in this direction pushing against that piston. Now, that is an assumption that we're making, but it's a close enough assumption to be allowable. Enthalpy is something that we can measure if we have a process taking place at constant pressure, right? Because then we can get rid of that, some of the concerns associated with like changing pressure. So in chemistry, we try to study, well, actually in thermodynamics and physics as a whole, all the processes we study pretty much take place at constant pressures. So we assume the only work being done is that pressure volume work, okay? And we can look at that and figure out the heat flow by measuring enthalpy. So what's enthalpy? Enthalpy is H, right? And it is the energy, that same E from a minute ago, plus pressure times volume, all right? If the system changes at constant pressure, then the change in enthalpy, delta H, is equal to the change in the energy plus P times V. And so we can write that, right, if we distribute it through this formula right here. Make sure you know that formula. Now here's where we're going to get to some interesting math. If delta E is Q plus W, and we know that W is equal to negative P delta V, we can use algebra and do some substitutions, and we can find out that delta H is equal to Q, right? So I'm subbing in that work value, all right, and the Q plus W value for delta E here, and I'm getting that delta H equals Q, right? Because plus W and negative W cancel out. So at constant pressure, and this is really important, at constant pressure, the change in enthalpy is equal to the heat gained or lost. They are simultaneously equivalent, all right? If you're doing a positive, or if you calculate a positive delta H, then we, put that together with an endothermic reaction. We're gaining heat. If we have a negative delta H, that's an exothermic reaction, right? So calculating delta H will tell us, should we expect to detect an increase in temperature or a decrease in temperature when we're doing a certain reaction. Now, the change in enthalpy is another way that we can describe this, is the enthalpy of the products minus the enthalpy of the reactants, right? Because again, we're looking at final minus initial. So the enthalpy value here on the y-axis, I'm looking at a set of reactants. Sorry, I completely lost my train of thought there. A set of reactants up top, a set of products, right, down here on the bottom. So I'm combusting methane. I'm making CO2 and water. I can calculate the overall delta H based on those two things, right? Here's the delta H for this side. There's the delta H for that side, right? And when I do that, all right, I can figure out something called the enthalpy of the reaction. And since historically speaking, they usually did it with combustion, it's often called the heat of reaction or heats of reaction, okay? Now, when we get down to the nitty gritty and like what we need to know about enthalpy, number one, it's an extensive property. So it matters how much stuff you have. Delta H for the reaction in the forward direction is equal in size, but opposite in sign to delta H for the reverse. This is going to be important in a minute when we start talking about Hess's law, which I know we've mentioned before. The final thing we need to know is that delta H depends on the state of the products. So there's, potentially more delta H in the liquid form of something than the solid form or the gas form or whatever. So the state matters. And when you see the delta H table in your book, you'll notice it's organized based on solid, liquid, gas, right? Or sometimes just solid, liquid, depending on what they've got. Now, calorimetry is something we talked about in year one chemistry that operates on this basic premise. We can't know the exact enthalpy of reactants and products, but we can measure the overall delta H through calorimetry because we know that heat is going to flow from the reaction into the surroundings, right? If the reaction is hotter than the water in the calorimeter, or it will flow, from the water into the reaction if the reaction is, endothermic. The calorimeter allows us to calculate these values using heat capacity and specific heat. So heat capacity is the amount of energy required to raise the temperature by 1 Kelvin, which is the exact same as 1 degree Celsius. When you look these up, they're usually given in joules per gram Kelvin, all right, for specific heats. And when you find, when you look at that number, that's usually for a mole of that substance. So this would be for a mole of N2, it'd be 4.18 joules per gram Kelvin. Now, when we say specific heat, we are simultaneously saying specific heat capacity, the same thing. It's the amount of energy required to raise that temperature of 1 gram of that substance by Kelvin, okay? One we want to memorize, that would be the one for water. That's how many joules it takes to get water from 14.5 Celsius to 15.5 Celsius, exactly 1 gram. So when we look at specific heat, and this is a formula you should know from last year, right? Last year we said Q equals MC delta T. We said, yeah, this is the MCAT equation. Well, now we're going to rearrange it a little bit. We're going to say C sub S, which is specific heat. C is also specific heat, but C sub S is a more accepted unit. So C sub S equals Q divided by M times delta T. So we just rearranged this equation to help us solve for specific heat. Know how to do that. Know this equation. Then when we do our calorimetry, we assume constant pressure, okay? We know the specific heat for water in the vessel is 4.184 joules per gram Kelvin. And because of that, we can figure out delta H for whatever reaction we have going on in there. We can use a bomb calorimeter. I think a bomb calorimeter gives you a little bit better outcome, and it also lets you do some things that you're not doing in aqueous chemistry, right? So like this calorimeter would be good for an aqueous reaction, right? But a bomb calorimeter, I can put solids in here in this reaction vessel and combust them. That's what those two ignition wires are for. Because of the fact that we know the specific heat of water, the heat absorbed or released by the water is going to be an approximation, a very good approximation for the delta H for that reaction. A lot of times, remember, delta H equals Q. And so when we know Q, we know delta H, right? Those things go together. We know that the volume is going to stay constant, all right? And because of that, what we're really measuring is actually delta E, not delta H, but they're close enough that we can basically use them interchangeably. Now, Hess's law, something I mentioned a minute ago, is a really, really, really nice thing in chemistry, because if I wanted to calculate the energy associated with making and breaking bonds, I would have to do each individual reaction like over and over and over again. But because we know delta H for a whole lot of reactions, we can estimate delta H using what we know about published delta H values and some enthalpy properties. So Hess's law says this: if you take a reaction and you carry it out in small steps, then the delta H for the whole reaction is equal to the sum of the enthalpy changes for the individual steps. Basically, the distance from A to B is the same whether you go up the steps or you take the straight path. That's what they're saying, all right? Since delta H is a state function, the total enthalpy change depends only on the initial states of the reactants of the products. What does that look like? All right. Well, in order to calculate these things, we have to know the enthalpies of formation, which we identify as delta H sub F. That tells you enthalpy of formation. All right. You can look these up in a table. I'm not going to make you memorize delta H's. That would be ridiculous. So make sure that you mark this in your book. All right. This is going to be a useful table. And now let's actually look at one. Let's see what one of these looks like. So we're going to calculate delta H for the combustion of this meth propane. All right. So let me make sure that's propane, not propene. 1, 2, 3, 4, 5, 6, 7, 8. Yep, there we go. Propane. Okay. So we're going to burn some propane. Oh, there it is right there. Didn't see it. So we're going to take this overall reaction and we're going to imagine it occurring in 3 small steps. So the first is going to be the decomposition of propane into carbon and hydrogen. The second is going to be the formation of carbon dioxide from carbon, which we just broke down out of the propane, and the oxygen gas. The third step is going to be the formation of water. The hydrogen left over from the propane plus more of the oxygen gas makes H2O. So if we look at the three steps, we've got number one, the breakdown of propane into carbon and into hydrogen. Number two, the combination of graphite, right, carbon and oxygen to make CO2. Number three, hydrogen and oxygen coming together to make water. If I can sum those three equations, and I get my overall reaction, I know I did it right. So how am I doing that? You look at what's on both sides of the reaction errors, and you cancel out like terms. So 3 carbons, right? This one's on the product side. This one's on the reactant side. I've got, let's see here, 4H2, 4H2, right? That's a product. That's a reactant. Cancel it out. 1 propane. I've got 3 plus 2 gives me a total of 5 oxygens. All right. I've got 3 CO2s and I've got 4 waters. So these steps add up to that. And that's the essence of Hess's law, right? We're breaking down a complex conversion into simpler reactions. Now, Hess's law tells us that the sum of the enthalpies of formation of the products minus the sum of the enthalpies of formation of the reactants is going to equal delta H. There are 2 other figures in here, N and M. They are the coefficients that go with the balanced equation for the products and reactants, respectively. So let's get that, right? If I go to that standard enthalpy table and I pull out the numbers for those little simple reactions, I can start to plug in my math. And when I'm done, there's the enthalpy for my overall reaction. And that's a really useful skill, all right? So you're going to do a couple of those. It's new. Make sure if you have questions, you ask. Something to look out for. Sometimes in that enthalpy table, it'll give you the reaction in one direction, but you need it in the other. Remember, that means you need to flip the sign. All right, that's important. Now, when we kind of scale this out of chemistry, we look at, how can we use this in the real world? Like if you're not a chemistry major, what can this equate to? Well, if you're a nutritionist, right, a lot of the energy in our food comes from carbs and fats. And if you burn those foods, you can do some basic calorimetry and calculate what their enthalpies would be, which is, useful if you're a nutrition major. You can also use it in the industries that look at fuel consumption, right? So, burning wood or burning coal or burning oil or burning hydrogen, right? Look at the fuel value for burning hydrogen compared to everything else here. That's kind of, important, right? You could find a more useful fuel for whatever you're doing. You can look at it in terms of renewable energy versus non-renewable energy, right? So at the moment, nuclear power, in 2015, when this book came out, nuclear power was providing 8.5% of the energy in the U.S. I actually don't know if it's gone up or down, but we can calculate like the number of joules produced in a year, and you can actually break it down into a monetary value if you really like to do a little bit of fancy math. So you can scale this out to the real world. We're going to kind of keep it in-house with thermochemistry, all right? Now, I know that was a lot. If you have questions, please send me an email. We can meet on Google Meet. You can talk to me through Remind, whatever, and that way we can figure out how to help get you through this, all right? So feel free to reach out if you need to.